Seaton from Daresbury Laboratory to talk to us about large-scale modeling with DL-Meso.
Okay, so welcome everybody. As Sarah said, I'm here to talk about mesoscale modeling and the code I developed, which is DL-Meso. Obviously, I'd like to take this opportunity to thank Sarah and the team at CCPBioSim for inviting me to talk to you today. I've also put some icons of put some sort of logos of various sort of communities and groups involved here who are involved with sort of DL-Meso here. So DL software is the sort of collective software that we develop at Daresbury, including packages like DL Poly and DL Monty. There's COSEC, which is the Computational Science Centre for Research Communities. CCP5, which is the collaborative computational project for computer simulation of condensed phases, and then there's also the high-end computing consortium UK COMES, which is the consortium on mesoscale engineering sciences, who actually fund some of the development of DL-Meso. So I'm going to just give you a quick overview of what I'm going to be talking about today. So I'm going to introduce you to mesoscale modeling and also to DL-Meso. And then I'm going to go into a little bit more depth about the actual mesoscale modeling techniques included in DL-Meso. So Dissipative Particle Dynamics, or DPD, and the Lattice Boltzmann Equation, or LBE. And I'm also going to give you some information about the practical exercises I've set for you today. The link for those is also on this slide here. So the link at the bottom, the web link at the bottom there. And I'm more than happy for you to sort of go to that, sort of visit that link now and take a look while I'm talking. So let's start with actually looking into what mesoscale modeling actually is. It's essentially that we're talking about forms of modeling of various kinds of materials and processes that operate at scales between those used in those scales in sort of atomistic kind of modeling approaches, so things like classical molecular dynamics, and continuum methods, so methods like computational fluid dynamics. Now, the diagram I've shown here is probably one that's at least vaguely familiar to everybody about showing the different techniques and the different sort of length and time scales in which they operate. One thing to note is that at the mesoscale, we actually are trying to sort of get kind of the best of both worlds of atomistic and continuum modeling. So we're actually trying to get the thermodynamics of our material right, but we also want to ensure that we actually get the right kind of flow behavior or hydrodynamics. So any kind of mesoscale model, we need to be able to actually obtain both atom-like and fluid-like effects in that same model. And the reason why we might be interested in modeling in mesoscale is the fact that a lot of fairly complex and interesting systems can act in at those sort of length and time scales, and can actually be modeled there as well. So a few examples I've got here. So things like looking at surfaces and interfaces between fluids, looking at how fluids that are dominated by capillary effects behave. So that's sort of microfluidics. Biological membranes are also, in terms of atomistic simulation, pretty large scale structures, but those can also be modeled at the mesoscale as well, and there are also things like phase behavior as well. So, and actually one thing to note is that the two techniques I'm going to be talking about, DPD and Lattice Boltzmann, they both fit into that mesoscale, but they are kind of on almost opposite sides of it. So DPD is probably closer to sort of atomistic or coarse grain MD kind of scales, and Lattice Boltzmann is closer to the kind of computational fluid dynamics kind of sizes and times. So there are two. So the main approaches for modeling at the mesoscale are we're actually going to be modeling some form of particles or beads, as I'm going to call them, and see how those move as time progresses. And there are two main approaches here. So one of them is actually fairly similar to classical molecular dynamics, the technique that you've been sort of looking at for most of this week, which is to actually calculate interaction forces between the particles in your sort of simulation, and then integrate those forces over small periods of time, small steps in time. So this is actually, this is obviously this approach is actually a time discretization. But the other approach is actually, rather than considering exactly where each particle is, to actually look at the likelihood of finding particles. And those particles will actually collide with each other and move. And in the case of Lattice Boltzmann, they'll be moving on some kind of regular grid. So we're actually, in this case, we'd actually be discretizing both in time and space. And one thing to note is that the beads or the particles here that we're considering in our mesoscale model can either represent, they could either be similar in approach to coarse-grained molecular dynamics, in the sense that each particle can be a certain number of atoms or a certain number of molecules or certain segments of a larger molecule. And each of those beads would represent what we would describe as a sub-thermodynamic population. But the other approach, the other representation a bead can have is to actually be a mesoscopic representation of a continuum fluid at the mesoscale. And in that sense, there's in that particular approach, there's actually no direct correspondence, or there doesn't have to be a direct correspondence to the actual atoms or molecules that you're modeling. So that approach could be used for looking, for modeling, say, a solvent in some kind of mixture, for instance, where we're just considering the solvent as some big mass of liquid. But then there's also how we set up our mesoscale model, and the biggest challenge for us here is to actually find the interactions between the beads that we're modeling. And there are actually two approaches here. So one of them is to carry out what's known as coarse graining, or do a kind of bottom-up approach, which is to say, well, we have each of these beads has some atoms within them, and we know how those atoms interact from say our sort of the potential that we use in molecular dynamics. And let's try and find some kind of effective interaction between the two beads, as which could be some kind of averaging of those microscopic interactions between the atoms. The other approach is actually a top-down approach, where we actually, have some kind of macroscopic behavior we want to replicate. And so we actually choose our interactions, or reverse engineer them, to actually obtain that required behavior in those mesoscopic beads. And actually in the process of doing that can actually give us some additional kind of insights for our kind of system. And typically when it comes to sort of mesoscale modeling, we actually usually have some kind of combination of the two different approaches. So some aspects of it may derive from the microscale, but others might derive from the macroscale. So I'm going to leave you hanging there and now jump to actually talking about the code I developed, which is DealMeso. So DealMeso is a general purpose mesoscopic simulation software package that I developed at Dahlsbury Laboratory. And it consists of mainly of a couple of codes for the two sort of mesoscale modeling methods I've mentioned so far. So Dissipative Particle Dynamics, or DPD, and the Lattice Boltzmann Equation, LBE. And those codes are actually, they've actually include parallelization using NPI. So it means you can actually run these codes on multiple processor cores. There's also some multi-threading available for those codes as well. So that's another way to actually accelerate the calculations you want to carry out. Now, this code package was actually created back in 2004 as a flagship project for CCP5, and its current development is still being funded via COSEC for the high-end computing consortium I mentioned before, UK Commerce. The current version of the code is version 2.7, which was originally released back in December 2018, and it is actually a code. These are actually codes that are used quite widely by academics and industrial researchers. So there are at least 250 registered users of this version of DealMeso, and there have been more than 120 citations of DealMeso in articles, proceedings since 2012. So you've probably been through some of this already, but the main sort of requirements to actually install DealMeso on your own computers are actually just compilers for Fortran and C++. The Lattice Boltzmann code is written in C++, and the DPD code is written in a reasonably modern form of Fortran 2003. There are also some additional utilities written in both languages to prepare your simulations and process the results to allow you to visualize what has happened and to carry out some analyses. There's also a simple graphical user interface that was written in Java to help you write and edit some of the input files. And that one is already pre-compiled, but you do need a Java runtime environment to use it, although that is typically usually available on any kind of computer anyway. If you have MPI available, you can use that with the Lattice Boltzmann and DPD codes in DealMeso and exploit what parallelization known as domain decomposition, which is essentially the essential basis of this is actually dividing the simulation volume or the grid points as equally as possible among the available processor cores, and each core can work on its own section autonomously, but it will need some communication with its neighbors in order to complete the calculations. But that means it means that you can actually carry out a calculation considerably more quickly. It's also possible to add OpenMP multi-threading to these codes as well to give you further speed up. And that's generally OpenMP is generally available with your Fortran and C++ compilers anyway, so you can just invoke that option. You don't need to use any external libraries beyond MPI for compiling these codes, although in the DPD code there are some options to use some external libraries like FFTW for fast Fourier transforms for some of the electrostatics, in place of some of the internal subroutines that are supplied with DealMeso. And also just for some further information and reference, so if you've been registering for DealMeso, you've probably visited the website. There's a link here that will take you directly will direct you to it, which is reasonably straightforward to remember. But there's also an article that we published back in 2013 about the code and what it does, and it's actually what we recommend you cite if you publish research based on running DealMeso. So now I'm going to go through both of the mesoscale modeling techniques that are available in DealMeso, and I'm going to start with Dissipative Particle Dynamics (DPD). And the reason for this is that it's actually, in terms of how it actually kind of works, is actually very similar to classical molecular dynamics. In essence, they're both DPD and molecular dynamics are doing basically the same thing. So you're modeling particles moving around, and these particles interact with pairwise potentials, and those potentials give you forces that you can actually calculate, and then you can integrate the forces acting on each particle to move it around. And because DPD and molecular dynamics operate in a similar kind of manner, you can actually, if you want to carry out some analyses on the results that in a similar way to molecular dynamics, to similar things that you carry out in molecular dynamics, you can with DPD. So many of the same kinds of sort of analyses that you can carry out with MD will work with DPD as well. However, the two big differences, one is that there's actually a kind of thermostatting in DPD almost for free. So there are actually additional dissipative and random forces that act between the particle pairs, and those forces not only control the simulation temperature, but they also automatically conserve the momentum of both of the system and locally. So this gives you a property known as Galilean invariance, which is basically to say that any kind of large-scale fluid property will be the same regardless of the frame of reference that you use to measure it. And what that means is that you will get that you get the correct that it will give you correct hydrodynamic behavior for your particle system, even if you are using a small number of particles. The other difference with classical molecular dynamics is the fact that we actually have a fairly flexible approach to what the beads can be. So these can either be our sort of coarse grains, or they can be our representation of a continuum fluid, so what are known as carriers of momentum. And also that these beads will actually typically have soft and repulsive interactions between them. And the effect of that will actually help us increase the time steps that we can use compared to classical molecular dynamics, which means we can actually obtain say sort of steady state or equilibrium structures considerably more quickly. So going through the algorithm itself, so the first part is the thermostats. These are two additional forces, and actually the technical definition of DPD are these two forces. So the first of these is a dissipative force, which kind of gives something like viscous drag, applies a kind of viscous drag to the system. And then the other is a random force, which kind of adds something like Brownian kind of motion to the system. So the forms of those forces are shown here. So we have gamma and sigma as our sort of parameters for each of the forces. Then we have these functions W, which are some kind of what I'm going to call screening functions, which are basically functions of the distance between the two particles in a pair. And then for the dissipative force, we have the dot product of the unit vector and this quantity here, which is the relative velocity between the particles, essentially just the difference in the velocities. For the random force, instead of that dot product of unit vector and relative velocity, we have this term, I think it's called xi, which is actually a Gaussian random number. So it's a random number that fits into a Gaussian distribution with zero mean and variance or standard deviation of 1, which we then divide by the square root of the time step we're using for integrating our forces. Now that sort of random number and square root of time step together gives something what's known as a Wiener increment, but we don't need to necessarily know about that now. But the point is that these two forces will work together as a momentum conserving thermostat, but the conditions for them to do so, and also to not affect any kind of equilibrium structure of our particles that happen to form, So the two conditions are that the screening function for the dissipative force has to be the square of that for the random force. And the other is that the square of the random force parameter is equal to 2 times the Boltzmann constant times system temperature times the dissipative force parameter. So it means that we do actually have temperature control. And one thing to note is that the gamma, the dissipative force parameter, can be related to a fluid's kinematic viscosity. Although I should point out the relationship between gamma and that viscosity is actually fairly complicated. But that's not too much of an issue for us to actually use this thermostat in our simulations. The other point are the conservative interactions, the actual interactions between the thermodynamics essentially for our simulation. Now, DPD as a whole does not actually apply any kind of restriction to what those interactions should be. However, the most frequently used form was one that was devised by Robert Groot and Patrick Warren back in 1997. And it takes the form of a pairwise interaction force here, where you have a conservative force parameter Aij, a linear function of the distance between the pair of particles, and obviously a unit vector. And that linear function goes to 0 at a set cutoff distance or interaction length. And any pair of particles that are further than that cutoff distance apart will not interact. Now the effect of this, it gives you a quadratic form of the interaction potential between the particles, and you can see that in the graph on the right hand side here, with the red line is that sort of Groot-Warren potential as compared to a Lennard-Jones potential shown here. And you can the other thing is that this form of interaction force will also give you a quadratic equation of state. So the pressure of your fluid will at least partially depend on the square of the particle density. And this means that although it's not necessarily a particularly realistic equation of state, it means that we do have some non-ideality compared to, say, an ideal gas. The other point is that, as you can see from the potentials here, the potential actually goes to a finite value at 0 separation, and it's also completely repulsive. So it means that because this potential is pretty soft, it means that we can actually use a considerably larger time step than classical molecular dynamics simulations typically can. So it means we can get to an equilibrium state more quickly. So before we go on, there are some, when we carry out a DPD simulation, there are some fundamental units that we have to consider, and there are usually 3 quantities that we set to 1 during a DPD simulation. So we have a mass unit, a length scale or a length unit, and an energy. And typically, the mass unit will be the same as the mass of a particular DPD bead. The length unit will be the interaction cutoff distance, which is related to the bead volume. And then the energy level is basically Boltzmann constant times temperature. And so I've got an example of it. I've got an example here for water at room temperature, where we're assuming there's 1 molecule per DPD bead, and we're also using a bead density of 3. So it means that the equation of state I showed in the previous slide will definitely work. And you can see that so we have the mass unit is equal to the mass of a water molecule. The length unit is equal to can be related to the volume of a water bead multiplied by the bead density that we wish to use, and that's of the order of about 4.5 angstroms. And then we also have an energy unit there as well. Now, a couple of things to note is that our system temperature, it can be related to the kinetic energy per particle. That's actually pretty typical also of classical molecular dynamics. But also we can derive our time unit in a couple of different ways. So one way to do this is to actually go from our fundamental, use a combination of our fundamental units. So the length scale times the square root of mass over energy. And in the case of our water bead, that gives us around a time unit of around 1.2 picoseconds. The other way, though, is to actually compare the diffusivity of the beads in the simulation to an experimental value for the fluid, and that can give us an alternate time unit, which is actually another order of magnitude higher. So it means that, you know, even if we are using a fraction of that time unit in our time step, that's going to be at least an order of magnitude, if not more, than the sort of time steps that we typically use in classical molecular dynamics, which are usually about a femtosecond. So yeah, 10 to the minus 15 seconds. But we can certainly use at least 10 to the minus 14, 10 to the minus 13 seconds as our time step in DPD. So some of the things that we can do with DPD, and one of the things we can control very much control, are how the beads interact with each other. And so there are two things that we can use to help us determine what the interactions between our beads should be. So if we're considering beads of the same type, so beads of the same species, particle pairs where each particle is of the same species, both particles are the same species, the interactions between those will determine the compressibility of the fluid. And indeed we can parameterize for that using the equation of state I showed a couple of slides ago. But then the other group of interactions we need to consider are between the different species, and those can actually control effects like hydrophobicity. So for instance, how much a bead wants to be around water, say. Now, there's no single best method of parameterization in DPD, and actually a number of papers on that study systems with DPD sometimes just sort of pluck parameters almost out of thin air. However, there are some systematic approaches available that do get used. So one of them is actually a connection to something called Flory-Huggins solution theory. So we can actually define a parameter chi, which is linked to the free energy of mixing between two components. Now, this assumes that all interactions between beads of the like interactions between our beads are all the same. But it means that if we have values of chi between different pairs of components, we can actually get the conservative force interaction parameters between those pairs of components. And it's actually there's actually a proportionality there. There's also another approach which is actually similar, which is actually to use infinite dilution activity coefficients instead of chi parameters, Flory-Huggins chi parameters. And actually the activity coefficients are something that it is also possible for us to predict for particular fluids, either from experiment. We can either get them from experiment, or they are schemes like UNIFAC that allow you to predict what the activity coefficients between two components of various molecules could be. Another approach that we've actually used at Daresbury, actually in the Hartree Centre, has been to actually fit parameters to give what are known as water octanol partition coefficients. So these are essentially ratios of concentrations of a particular component in different liquid phases. In this case, water and octanol. But that involves actually carrying out a large number of very large simulations. But it does mean that we can get sort of it is still a systematic way of obtaining the parameters we need to represent our bead interactions. Another thing we can do in DPD, which actually really does sort of expand what we can do with the method, is to actually include bonded interactions between beads, particularly those that have different interaction parameters with different components. So it means that we can construct molecules like amphiphiles and lipids, and I mean, it's not just a case of putting springs between pairs of particles. We can also control bond angles and dihedrals. So I've got an example here on the left-hand side, which is of a 4-bead amphiphile of one hydrophilic head, one bead that likes to be around water, and a hydrophobic tail, the three beads here that want to stay away from water. And I can show you a simulation of a solution of those in water, where I'm not showing the water in the movie here, but you can see that those molecules do actually spontaneously form into a larger structure. In this case, it happens to be a vesicle, which is like a bilayer, a spherical kind of bilayer that actually incorporates some of the water inside. So, and if you take a slice through it, slice through the vesicle at the end, you can see there's water right in the middle of it. And the other simulation I've shown here, which is not a video, but it's actually, we've just extended the amphiphilic molecule to give us effectively like a lipid, but we can also control the angles between the bonds here, and that ultimately gives us, can give us a lipid bilayer, as you can see in the diagram on the right. But we can go, and actually those two capabilities, the parameters that we set and the bonded interactions between the beads can allow us to do quite a lot already. But we can go even further. So we can also apply charges, electrostatic charges, to our beads as well. And obviously these involve longer range calculations than the pairwise interactions that we've been looking at so far. And we can use various sort of Ewald summation techniques or particle-particle-particle mesh techniques and all sorts of other kind of Poisson solvers. However, one thing to note is that because we're typically using soft repulsive potentials between the beads other than for charges, there's a risk of opposite charges collapsing on top of each other because those repulsions may not be enough to keep the beads apart. So more often than not, we actually have to apply some kind of charge smearing to those charges to avoid these particles landing on top of each other and not being able to pull away. One practical aspect of this is that if we're using something like Ewald summation to calculate our electrostatic interactions, we can assume that this smearing only affects the real space part, the short range part. And the example I've got here is of a hydrophobic polymer. The top one is actually a polyelectrolyte, so each bead has the same charge on it, and then the system at the bottom is of just that hydrophobic polymer, and you can see the effect of adding the charges on that polymer means that it actually opens up, and you can actually be able to show that by measuring the radius of gyration of that molecule. It's also possible for us to include charge polarizability effects by adding charged dipoles to our simulation as well. So we can so it's possible to attach charges to neutral beads, for instance, and actually incorporate some polarization. Although that's a fairly new kind of area for DPD. Other things that we can do are actually use various types of boundary conditions. So we can carry out DPD simulations in periodic boxes, but we can also apply various forms. We can also apply shearing using what are known as Lees-Edwards conditions. We can also have sort of hard planar surfaces, which can also include additional wall potentials. And we can also freeze some particles in position to create a kind of walls. We can create walls using these frozen particles, although we often have to use some kind of reflective boundary as well to ensure that fast-moving particles don't penetrate the walls. And an example of one very simple example of what we can do with that is actually to have two sort of frozen B walls and apply a constant force on the particle, on sort of fluid particles in between them, and that will give us a pressure-driven, effectively the equivalent of a pressure-driven flow between the solid plates, which gives us a velocity profile that's not too dissimilar to what you would get from, say, a computational fluid dynamics approach. There are also some alternative interactions that we can apply between pairs of particles. So we can actually use our molecular dynamics potentials with the DPD thermostat, for instance. And that's something you may want to consider if you're looking at systems with flow fields. The other possibility is that there's actually a field of what's known as many-body DPD, which is essentially where we actually calculate localized densities for each bead and use those densities in our interactions. So it means that you can actually change the equation of states that those beads have, so that fluid has. And it means you can get behavior, behavior for multiple phases, including things like liquid vapor equilibria. And I've got another example of here where we have water drops forming on a hydrophobic surface under the influence of gravity. So if I play the video, you can see the particles forming into drops, and those land on that surface. And you can actually control by controlling the repulsion between the water and the particles in the wall, you can actually control that contact angle between the wall and the drop. Other things that we can do with GPD are actually looking into better ways of applying a pairwise thermostat. So one of the limitations of the GPD thermostat is the fact that how well it controls the system temperature will depend on the size of the time step that you use. And there's also another problem with it is, as I mentioned, there was a complex relationship between viscosity and the dissipative force parameter. And that relationship, the relationship is shown in the graph here. But the other thing to note is that range of viscosity is typically more typical of gases than liquids. So there are a few things we can do. So one of them is a simple one, which is basically recalculate the dissipative forces after we've integrated all of the forces that we've calculated before in each time step. And that has because that's such a common a commonly used sort of approach, that's actually given the name DPD velocity Verlet. Another approach is to actually integrate the dissipative and random forces in DPD in a smarter way. So techniques such as Chardley splitting, which actually effectively integrate those forces before calculating and integrating the interaction forces. But then there are also some other pairwise thermostats available that actually apply changes to the velocities of pairs of particles after force integration. But a lot of these also have the effect of boosting the possible viscosities that you can actually use. It's also possible for us to actually not just have constant volume and temperature ensembles, but we can also include barostats. And we can actually couple all of these thermostats to some form of barostat to control system temperature, the surface tension across, say, liquid bilayer, for instance. And before I move on to the actual code in DL-Meso, I'm going to say there's some, that DPD has been used for quite a few sort of biomolecular and biological systems. So there've been DPD simulations of blood, where the actual red blood cells have been represented using some kind of networks of bonds. Then there's also been studies of proteins with charge polarization, and there's actually a kind of a model of adding charges to particular beads in a protein and in a solvent, which is actually fairly similar to how the Martini coarse-grained molecular dynamics force field actually kind of works. There have also been simulations of biological membranes. So things like the example shown here, deformation of bilayers by proteins. And then there's another example I'm going to show in a little bit more detail, which is loading and release of drugs in vesicles. So in this case, we've got a copolymer, polyamino ester and polyethyl glycol, sorry, in water. And there's also an anti-cancer drug, camptothecin. And the way in which this model was parameterized was they actually carried out classical MD simulations of pure and mixed components, and used the energies from those to obtain Floyd-Huggins chi parameters, and then used the relationship between chi and the conservative force parameters to get the conservative force parameters for DPD simulations. And the parameters they obtained were basically these here, and they actually carried out two sets of simulations, one for a higher pH where the drug would be loaded into vesicles, and the other where the drug at a lower pH where the drug would be released from those vesicles into solution. And one thing to note is that they actually obtained different conservative force parameters for the polyamino ester between that component and other components. So it becomes considerably less hydrophobic with water, but it repels the camptothecin more than it did before. So we actually carried out carried out a DPD simulation of this system as a kind of test. So we start here with the loading of the drug into vesicles. And then when we got to the end of that simulation, which was about 900 nanoseconds in actual time, we used the end point of that simulation as a starting point for the drug release simulation, which is about to start now. And you can see that the effects of changing the interactions between polyamino ester and everything else means that those vesicles actually swell, break open, and push out the drug. And the people who actually carried out the original research found that the amount of camptothecin being loaded into the vesicles actually matched experimental observation. The actual DPD code in DL-Meso does pretty much what it says here. It will actually calculate the interactions between beads together along with a pairwise thermostat, which is normally DPD, but it could be some of the others I briefly mentioned before. It uses the mean decomposition as its main form of parallelism. And there's a technique it uses to efficiently find interacting particle pairs within a cutoff distance. You can also apply OpenMP multi-threading to actually speed up those force calculations as well. If you've ever used DL-Poly, particularly DL-Poly 4, the DL-Meso DPD will work. It actually works in a similar manner, although they're not directly the same code, and in fact they do share a common kind of code ancestor, but they have been developed kind of separately. But also DL-Meso DPD comes with a number of sort of pre and post-processing utilities to help you set up some simulations, visualize and analyze your results. So the various functionalities that exist in DealMeso DPD include various types of interaction potential, various kinds of pairwise thermostats, various kinds of bonding interaction, a couple of techniques for applying electrostatics, which are based on Ewald summation. But also those include some different ways of applying charge smearing to beads to ensure opposite charge particles don't collapse. There are also a couple of different kinds of barostats available, so you can carry out constant pressure, constant surface area, constant surface tension ensembles. And there are also different kinds of boundaries, including some with wall potentials as well. And so the various input and output files that you use and obtain, use for DealMeso DPD simulation and obtain from as a result. So you have two that are absolutely essential for controlling the simulation and specifying interactions. The code will actually come up with an initial configuration for you based on the control and field files, but if you want to supply your own, you can in a file called config. And there are also a couple of files for simulation restart if you want to resume a previous calculation. What you get out of it are a simulation summary in a file called output. You can optionally get some sort of tabulated system properties for later analysis. There's a file for simulation trajectories, and then you've got two files for simulation startup, a configuration and then accumulated statistics. And then you can also get a couple of optional other sort of outputs. So you can get the stress tensors to analyze more, to carry out some more advanced kind of flow analyses, and also, and if you've allowed DealMeso to create its own initial configuration, you can actually write out what that is for future for a future calculation. And to carry out a restart, you basically use the export, at least the export file, but you can also use the revive file if you want to preserve your accumulated statistics from before. If you want to start a new simulation from a previous simulation, you've got a few different options. You can either take a frame from the simulation trajectories in history, or you can use the configuration from a simulation restart. Both of those you can process through a utility to give you a new config file, or you can take the generated simulation setup from the config ini file, rename that as config for a new simulation. The two main files, input files, look a bit like this. So you have the control on the left and the field file on the right, and they're both based on keywords to identify simulation or interaction properties and values, and hopefully reasonably readable and understandable. And as I said, you can actually start a simulation without supplying an initial configuration. So you can specify what the simulation volume is in the control file, but in the field file, it gives you the numbers of beads and the numbers of molecules, along with the positions of those beads in each molecule type as a sample to throw into your simulation box. And these files are actually easy to create or edit by hand in your favorite text editor, but the graphical user interface, the GUI, can help you do that as well. And then the output files that you get, the ones that are readable are the output file, which gives you the summary of the calculation both what you've included in the input files and as the simulation progresses. And then the file call gives you the values of particular sort of properties that you at given points in time. Although the other major file that you might want to use is that the history file is actually in binary, and as is the export file. But but there are some utilities available for you to actually read and convert those files into other forms so you can analyze what's there, visualize, or start a new simulation. And actually, the reason why that the formats they are is because I'm not tying those trajectories to a single visualization program. So it means that you can use VMD or a beta or something else if you want to. Okay, so I realize I'm sort of running out of time, but I'm going to try and go through the Lattice Boltzmann equation. So this is actually, as I mentioned before, this is actually a fairly different approach to modeling how particles move. So rather than worrying about where a particular particle is at a given point in time, we actually want to know the probability of finding particles. And the particles are going to move based on how they based on them colliding together and then propagating or free streaming around. Now, to help us actually make the calculations feasible, we're actually going to limit the possible momenta each particle could have. So it means that the particles can only move, say, from point to point on a grid. However, we can show using quite a lot of mathematics that this kind of simple model can still correctly model macroscopic fluid behavior, and we can show that what we're modeling can actually essentially gives us the Navier-Stokes equations of fluid flow, which means that these particles do behave like a real fluid. There's also a fairly flexible definition of what the particles are. Now, these are usually, in Lattice Boltzmann, these are usually closest to the kind of carry of momentum kind of approach. So we're not necessarily tying them to particular numbers of atoms or molecules. However, it's still possible for us to include additional interactions between these particles through actually how they collide to actually represent microscopic behaviors and actually get the right kinds of thermodynamics. So the way Lattice Boltzmann kind of works, we're going to define something called a distribution function, which is a function of time and position and holding a particular momentum. So this is the probability of finding particles at that time position with momentum. Now, the evolution of that distribution function is given by the Boltzmann equation, and I'm showing a very simplified version of it here. But what we're going to assume is that the collisions between, so I should say the left-hand side of that equation is essentially like the free streaming or propagation. The right-hand side is the collisions. But what we can assume is that the particle collisions are pairwise and they're not correlated. The particles are not correlated before they enter a collision. Now, that's normally only true for low-density gases, but it does simplify our link between Lattice Boltzmann to the Navier-Stokes equations of flow. And also, because our definition of what a particle in what we could describe as a lattice gas is fairly flexible, it means we can actually still use this approach for liquids as well as gases. And obviously, we're restricting our particle motion to a regular or regularized grid where we're defining links between the different points. So we have a series of links with the subscript I here, and we can actually conflate our distribution functions. So we actually have we can actually say we have distribution functions for each distribution function for each given link given the position and time. And the evolution of those distribution functions can be given as separated collision and propagation steps. So the collision is basically for each distribution function, for each link's distribution function, we can apply what we could describe as a collision operator, C underscore I, and that gives us a distribution function at a time just after the time we're currently on, so the time after collisions. And then the propagation, we just simply move that distribution function along the lattice link to the next grid point, and that takes us to the end of the time step. And we can actually calculate the macroscopic fluid properties by summing up, finding moments of those distribution functions. So if we consider a particular grid point, if we sum up all the distribution functions over all the lattice links, that gives us the macroscopic density of the fluid. If we multiply those distribution functions by their link vector first before summing them up, that gives us the density times the velocity of the fluid. Now, there are different ways of applying there are different collision operators available, but the most frequent way we carry out collisions is to consider a deviation from something called a local equilibrium state. And we can actually work out what the local equilibrium distribution function is based on the density and velocity of the macroscopic fluid. So for each particular grid point, we can work out what the density and the velocity is, and then calculate the equilibrium distribution function. And then the simplest form of collisions basically takes the deviation of the distribution functions from equilibrium and divides it by a single relaxation time, tau. And that's basically the collision operator for that link. And it goes by an approach, it's known as, the approach is known as Bagnarsson-Gross-Krug. Now, you can consider that collision as a kind of numerical representation of particles colliding together at particular grid points. And so it does, although it is effectively a numerical approach, it still makes at least some kind of physical or chemical sense. Now, the thing is that relaxation time can be directly related to the kinematic viscosity of our fluid. So this is actually one property that's particularly important in a Lattice Boltzmann simulation. The reason for that is that it actually helps us determine how the actual size of our how big the simulation, how big the system we're modeling happens to be. Because there are three quantities that we can set, which are the lattice grid spacing, delta x, the time step delta t, and the fluid density, although that happens to be a relatively free parameter in our calculations. Now, there are actually two properties that we can determine from the grid spacing and the time step, and those are the speed of sound, which is set to 1 over the square root of 3 times the grid spacing divided by the time step, and the other is the kinematic viscosity, which is the which I showed you the expression for before. And it means if you set the relaxation time, you can actually specify what the grid spacing and the time step is if you know the speed of sound and the kinematic viscosity of your fluid. So there's the example here on the right for water. Although one thing to note is that it's best to set the relaxation time to ensure that the calculator is numerically stable, so not too close to a half. But it means that you do have you still have quite a lot of control over how big your system happens to be. Okay, so some of the things that we can do with Lattice Boltzmann, we can actually apply lots of different kinds of boundary conditions, and those are essentially the aim of those boundary conditions are basically to find some missing distribution functions that point back into a simulation box. But these can actually be determined in actually fairly simple and intuitive ways. So one very simple form of boundary condition that we can use is bounce back. So literally just reflecting the distribution functions back from where they came and doing just that. Okay, so there are more sophisticated methods of applying boundary conditions. So you can apply constant densities, constant velocities at boundaries. And you can also extend these to sort of boundaries that actually move through the lattice as well. So you could look at suspended particles in flow. However, even with just simple bounce back, you can actually look at sort of flows past obstacles like the one here, and observe various kinds of effects. If you're applying, say, a pressure drop along the length of this sort of channel, for instance. So that's an example of something called a von Karman vortex street, and actually happens to be one of the practical examples later, although it's actually optional for this workshop. Okay, another big feature of Lattice Boltzmann is that it can actually model multiple fluids and phases pretty easily. So the way it kind of works is that we can actually calculate interaction forces at each lattice site and apply those forces in the collisions. Now, those forces are generally dependent on gradients of fluid density or some other similar property. And actually, we can get very good approximations of those gradients using grid point stencils. So actually, obtaining, as I said, so obtaining the gradients is that, we can obtain pretty accurate gradients. And as I said, it's possible for multiple fluids and even multiple phases to coexist. In the case of fluids, we can actually have separate lattices that occupy the same space, and each fluid is modeled separately on each lattice, although we couple the fluids together using the interaction forces. So those interaction forces will determine how each fluid will move. And one thing to note is that the interfaces between the fluids and the phases will emerge, so we don't actually have to explicitly track where they are. So it means that, as I said, it's computationally inexpensive for us to actually model multiple fluids in Lattice Boltzmann. So I've got an instance here of a drop being dragged along by moving the top wall here, and you can see that it does actually not only deforms the drop and pulls it along to the right, the drop also lifts towards the center of that channel. But then there's another simulation here, which is actually of two fluids separating out from each other. And this is actually one that my mother has referred to as a lava lamp, and you'll probably be able to see why. But anyway, the point is that these, not only can we model multiple fluids, but these fluids can also have different equations of states from those for a standard lattice gas, and so it means we can actually choose the equation of state we want to apply to our fluids. Okay, so some more things that we can do with Lattice Boltzmann. We can actually also couple in diffusion and heat transfers to our simulations. So there's actually a simplified local equilibrium distribution function that we can use, and this effectively gives us viscosity dominated flows, or Stokes flows. So sort of fluids creeping around. So we can look at things like fluids creeping around objects, for instance. However, we can also use that approach for solid diffusion, or to represent some kind of temperature field in a bulk fluid. And we can actually, and the way we can do that is to model the solute or the temperature on a separate lattice and use the bulk fluid velocity in the above equilibrium distribution function to couple the motion in. Now, in the case of a temperature field, that gives us heat conduction. If we want heat convection, we would either need to, if you want to see the effect of the flows generated by changes in temperature, we would either need to specify a particular equation of state for our fluid, or we can actually add in a temperature dependent force. And there's something called the Boussinesq approximation that gives you a local force based on the temperature at a particular point in space. And that will give you effects like the Rayleigh-Bénard natural convection that you can see at the top right here, with a hot wall at the bottom, cold wall at the top. And you can see the sort of distinctive temperature profiles, but also circulatory flow. It's also possible for us with solid diffusion in our system. We can also add additional source terms to the solutes to apply various sort of reaction kinetics. So it means that we can also model reactions. We can also model actual reactors. We can also model combustion processes. So the one on the bottom right here is actually an example of a char pellet being combusted, and you can see the temperature field that results. Another thing that we can also do is actually apply non-Newtonian rheological models to our lattice Boltzmann simulations. And the way we can do that is we can actually include some kind of, we can actually change the viscosity or the relaxation time at each grid point. But to get that, we have to calculate the shear rate of a flowing fluid, and we can get that either by calculating velocity gradients, which requires a stencil that looks around surrounding points, or we can actually calculate that directly for each grid point on its own by calculating a local strain tensor, the value on the right, which is dependent on the deviation of the distribution function from equilibrium. And that, once we've got our shear rate, we can then use that, work out what the relaxation time should be at each grid point, and we can then model things like non-Newtonian fluids, like a Powell law fluids, shown with the velocity profile shown in the top right here. We can also look at viscoelastic systems, and we can also look at, we can even look at various sort of turbulence models as well. So we can actually apply turbulence to a fluid flow, such as the one shown here on the bottom right. So in terms of what we can do with lattice Boltzmann for biomolecular and biological systems, there are things like biomicrofluidics, which means we can look at things like, so we can actually look at systems where capillary effects have a major influence on flow, and in terms of sort of biological application, that includes things like seeing how drops collide with each other or land on surfaces, and also controlling the drops in various, how we can control the motion of drops in various sorts of medical diagnostic tools, for instance. There are also various sort of liquid and gas-liquid flows that we can look at, and I've got an example here of a flow of a foam going from left to right here. And then we can also use our multiple fluid algorithms and consider the interfaces between fluids as biological membranes. So it means that with a bit of tweaking, we can actually use our fluid models to actually model things like fluid field vesicles like red blood cells. And as an example at the bottom here of flow of blood cells through a constricted channel. And that's basically a slight modification of the algorithm used to look at the drop that was sheared before. So the lattice Boltzmann code in DealMeso, it basically, in essence, it solves a discretized Boltzmann equation on at least one regular lattice. It can be parallelized it's parallelized basically with domain decomposition, and you can actually divide the lattice among processor cores, but also among threads, making the point that actually the collisions are the most computationally intensive part of the calculations. But we can also specify, in our sort of DealMeso lattice Boltzmann simulation, we can also specify boundary conditions for walls and obstacles, some the initial conditions, fluid interactions, and so on and so forth. And there are various utilities available to help us set up simulations and collect together outputs created in parallel to analyze and visualize what we've modeled. So the various functionalities, we can actually model 2- and 3-dimensional systems. The numbers after in these sort of terms here, the number after D refers to the number of dimensions. The number after Q refers to the number of lattice links per grid point. The more you have, the more numerically stable it will be, but obviously the more time it takes to carry out the calculation. But those fluids can be either compressible or completely incompressible. We can also include mass transfers of solids or heat transfer or both. We have a few different collision schemes going from simple to more complex, but also more numerically stable and then we've also got various types of boundary condition. particularly bounce back conditions, and also fixing velocities, densities, or solid concentrations or temperatures. But we can also apply surface wetting if we're including mesoscopic interactions. And there are three basic types of interactions between fluids here. So we've got one based on calculating what's known as pseudopotentials, which are basically functions of density. There's one by a guy called Seger-Liszczuk, which is basically just ensuring you have the right interfacial tensions between fluids. And there's also a method to obtain the correct free energy functionals by a group in Oxford. Although that one only works for one or two fluids at a time. But there are also some non-Newtonian rheological models available, including a couple that might be useful for blood flow, for instance, the Casson and Karu-Yasuda fluids models. The input and output files you get from DealMeso LBE. So the two that you absolutely need are the ones for the simulation controls and the boundary conditions. The one for the simulation controls will give you basically the initial conditions across the entire box, but you can actually use the lbin.init file to actually specify grid points where that's not applicable. And you could also restart a previous simulation as well. What you get out from DealMeso LBE are you get messages in your standard output, or it goes to the screen. But you also get your simulation trajectory as a series of files of one of each of those three types. And you also get the configuration for a simulation restart, as well as a couple of files for gathering the outputs if you're running in parallel. Now, if you want to restart, you just literally use the lbout.dump file and include a directive in the lbin.sys file to actually tell it to restart. If you want to start a new simulation from a previous one, you basically use that same lbout.dump file to create an lbin.init file, but you have to use the utility to do that. And so the input files, the two really important ones look like these. So the lbin.sys file is based on various sort of keywords to identify the simulation property and then the value. Now, the first 10 I've shown here in bold are actually the ones you actually have to include for all simulations, but there's no fixed order in which they can come. So those don't have to come at the top of the file, for instance. And these are used to define various fluid properties, your interactions, which the values for the sort of speeds or densities and things for boundary conditions, and also includes what the fluid's properties are at the start for the entire system. It's actually it's not too difficult to actually create this file by hand in a text editor, but the graphical user interface is actually quite useful here. And then the file on the right, the lbin.spa file, is used to define the boundary conditions at the required grid point. So it's basically the coordinates of the file, coordinates of the grid coordinates, and then a code for the boundary condition type. And it's actually you can do that by hand, but it's actually it's much easier to create that in the graphical user interface. And then there's also another file which I've not shown here, the lbin.init file, which will override the initial conditions for the system at specific grid points. And that's pretty useful for if you want to add, say, a drop into your bulk fluid, for instance, for multiple fluid simulation. And the outputs, now the standard output just basically gives you a summary of the calculation and how it's going. Including it also at each sort of given time step, it gives you the total mass, the masses of each of the fluids, and also the momentum, overall momentum of the system to show whether there's a steady flow being developed or whether it's unsteady or what have you. But it also indicates how quick. It also gives you some timing, so you can see how quickly DealMeso LBE is actually running. Now, the lbout.dump file is the restart capability, and that actually stores the distribution functions at all the different grid points. And that's one big binary file. But you can convert it into the file for the kind of initial configuration for a new simulation, or you can even visualize that take a look at that, what the state of the simulation in that file using a utility. And then there are also some output. The output files you get, one generated at each of the given time steps, and there are 3 different formats available. So there's a structured grid VTK file, which is a default. There's also a legacy VTK, and then there's a format called plot3D, which produces a solution and a grid file. The thing is, all 3 of those formats can actually be read and analyzed using PowerView, the program I suggested you install for the exercise.